Hey everybody, welcome back to another round of physics, and yeah, let's get going. Last time we introduced a concept called Gauss's law for the electric field, and I warned you that Gauss's law is always true, it's just not always useful. And we saw that Gauss's law becomes particularly useful when we can choose a Gaussian surface that gives us some sort of advantage when calculating the electric flux. Namely, when the electric field is constant on every point on the Gaussian surface, or perhaps when the electric field is parallel to the n hat vector representing the direction perpendicular to the surface and outwards. I promised in that video that I would do an example problem considering the infinite line distribution, and we'll treat it both with a direct integration, and then we'll apply Gauss's law and see that we arrive at the same answer. So let's go ahead and get going on that. So let's pretend that I have a charge distribution, linear, and it has a charge per unit length of lambda. Now, one of the approximations I'll make is that when I choose a field point, and we'll say that this is, I don't know, a distance y naught, when I choose that field point, I am going to assume that the distance that the field point is away from the wire is really small compared to the overall length of the wire. So imagine this wire is a distance L. We will assume that y naught is much, much less than L. And therefore, the wire, if we were standing at that field point, the wire looks almost infinite. This is an idea that we'll use a lot, both in physics and later on in your careers, is that sometimes it's really hard to do finite objects, but if we can consider it to be infinite, it sometimes gets easier. An example every day. Standing outside, when you look around, you notice that the earth looks flat, right? Now, you know that the earth is actually a sphere, but because when you're standing on the surface, you're so close. In other words, a different way to say it is your height above the surface is much, much smaller than the radius of the earth. Because of that, the earth doesn't look round from our perspective. It basically looks flat. Okay? And in fact, you could go even further. It basically looks flat and it looks like it's infinite. It continues on indefinitely. Okay? It's only when we get into a rocket ship or a space shuttle and our height becomes somewhat commensurate. I won't say equivalent to, but our height is not small compared to our radius, that the earth starts looking round. It starts looking round and it starts looking finite. This idea that we're close to the wire so it looks infinite is completely analogous, but it'll help us do some of the integrations. It'll help generalize some of the results. Okay? Well, let's go ahead. The question is, what is the electric field strength due to this wire? Okay. And so we'll have to choose a couple of variables. First off, I'll go ahead and, without loss of generality, okay, I will assume that the field point lies on the y-axis, and I'll put the origin of the wire. And for sake of argument, we'll say that that way is x. Of course, right-handed coordinate systems, that means that our z-hat is actually into the board, but we don't need that for the sake of this problem. And now, let's go ahead and run through our ideas. First of all, we need the position vector of the field point. Good. And you notice that that's just simply y naught. Okay. And I will need the position vector of our source charge. Now, from our discussions about continuous distributions, we know that we can take this distribution and chunk it up into tiny segments, each segment having a width of dx. And because I will assume a uniform charge density for this problem, the charge contained in that tiny segment is simply the charge density times the width of the segment. Okay, so I'll put in dq here. That little line segment as well is located some distance x from our origin. And so in a very general expression, we can say that the source is located at x, 0, 0. Remembering that x is our integration variable. Well, now that we have that, our relative position vector pointing from the source to the field point is simply given by the position of the field point minus the position vector of the source. Or, if you prefer in triplet notation, this should be negative x, comma, y naught, comma, 0. Following the same song and dance, we now say that the infinitesimal contribution to the electric field is simply Coulomb's constant times the value of that charge divided by the relative position vector, and I'll put the magnitude here, squared, times the unit vector of the relative position vector. Well, let's go ahead and substitute in all our quantities. K, of course, is a constant. We've already had a brief discussion about dq being equivalent to lambda dx. We have our relative position vector, so finding the magnitude shouldn't be problematic. We apply the Pythagorean theorem. We square the relative position vector. And finding our unit vector is simply dividing the relative position vector by its magnitude. And here we could say, technically, we're done. Physics has stopped, but we still need to apply our mathematics to come up with a result. Now we're dealing with a vector. I say, oh, crap. Right? We have a vector. We will deal with it in components. Right? So let's go ahead. Let's go through and we'll integrate the x component. We'll go through and we'll integrate the y component. And then we'll have the final expression for our electric field. Of course, based on the fact that I placed the origin at the midway point of the wire, we already know the x components are going to cancel out due to symmetry. Well, let's go ahead. We have a vector expression. Let's go ahead and find the x component due to every individual piece of that line charge distribution. And we notice, okay, we have our k lambda dx. We had a negative x from the vector. And then combining the denominator, we have x squared plus y naught squared. And that entire quantity is to the 3/2. Of course, we need to sum up over the entire length of the wire. And so we'll run this from L over 2 to L over 2. And you notice that that entire distance ends up being a distance of L. Okay. Well, we could attack this several different ways. Of course, k, lambda, those are constants. And so I'll pull those out of the integral. We have a negative x k, oh, excuse me, not negative x. We have a negative k lambda integral of negative L over 2 to L over 2 x over x squared plus y squared naught squared to the 3/2. Now here's always a good place to mention. First of all, you should be running through integration techniques. Okay? Again, how the symmetry manifests itself in the mathematical expression for this component is the idea about an even or an odd function. Let me take a brief byline. An odd function is any function where if you put in a negative argument, you get a negative of the original function. Okay? This is what we call an odd argument. Concretely, let's say our function is x. You'll notice immediately that that function is odd. By this, I mean if I do f of negative x, that means that I have a quantity negative x. But because I have a multiplication, I could write this as negative 1 times x. And notice that this, just regular x, is my original function. I have negative 1 f of x. And lastly, we generally don't write the 1 in, so I get f of x. And therefore, I've shown that when I plug in a negative argument, I can arrive at the original function with a positive argument and then a negative sign out front. When this happens, again, we call those odd functions. So I should tell you what is an even function. An even function is any function where when I plug in a negative argument, I end up with the same value as if I had a positive argument. And so, as an example, we can check to see if the quantity x squared is even. Well, if I plug in a negative argument, that is the same as saying a negative x squared, or negative 1 squared times x squared. But x squared is my original function with a positive argument. So this is negative 1 squared times f of x. But negative 1 squared is just 1. And so I end up with f of negative x equaling f of x. Now, polynomials are often easy, but there are other functions that are also even or odd. For example, sine is an odd function. In other words, if I take sine of a negative angle, that will be the same as negative sine of the positive angle. Cosine actually ends up being even. If I put a negative angle into cosine, it is the same thing as if I did cosine with the positive angle. And we'll run into these, but sine, cosine tend to be very common. Please bear in mind, not every function is odd, not every function is even. A function like x plus x squared is neither odd nor even, right? X being an odd function, x squared being an even function, and so the addition of the two functions together is neither even nor odd. However, if I did a multiplication, when I take an odd function and multiply it by an even function, yeah, you see that you end up again with an odd function. Okay. So based on that, if sine is odd and cosine is even, what's the tangent function going to be? Yeah, very good. Odd. Since we're dealing with an integration, it's also good to think about what do these functions look like graphically. Okay. An even function will end up being symmetric about the y-axis. So if I plot a function and it's even, what this means is that if I have a value of negative x naught and I evaluate the function and get some value, you'll notice that if I plug in x naught positive, I will get the exact same value. That's what this expression means. And you can see that if I integrated over a symmetric range, say if I integrated my even function from negative x naught to positive x naught, you will notice that I basically get an area times 2. And so even functions have a nice property that when you integrate an even function over a symmetric interval, it is the same as going from 0 to the limit and multiplying by 2. Now, that doesn't make the integration any easier, but it does at least make the evaluation of the integral slightly easier. Oftentimes, it's more straightforward to plug in 0 when you're evaluating limits rather than some other number. Odd functions do not have this symmetry about the y-axis. Odd functions mean that for when I plug in a positive number, I plug in the negative argument, I get a negative value. And so what ends up happening for odd functions is that they are, what is it? I want to say that if you take the graph and rotate it 180 degrees, you end up with the same function. I'll plug in, for example, something like this. That is a terrible looking function. Let's get rid of this, let's get rid of that, and I'll do something like this. An odd function demonstrates that rotational symmetry. If you picked up that function, rotated 180 degrees, and plopped it back down, you'd still have the same graph. And you can see, again, if I have a negative x and I plug it in, or I take the positive argument, I plug it in, you notice that you differ by a negative sign. So f of negative x naught and f of x naught, you see if one's in the positive direction, one is negative. Good. From an integration standpoint, odd functions are wonderful, because you notice that if I were integrating this odd function from 0, say x naught to 0, I get some negative area. But when I go from 0 to positive x naught, you notice I get the exact same area, but positive. And that is particularly helpful when we have an odd function evaluated over a symmetric interval. We can immediately say that the integration is 0. Pretty cool, huh? Now that's a complete byline, but it's something that does come in handy. You need to be aware of it. We can look at the integrand here, and we notice that x is an odd function, but in the denominator we have an even function. And so the division of an odd function by an even function gives us an odd function. Incidentally, if you don't believe me, go and check it. But this whole function is odd, and an odd function evaluated over a symmetric interval gives us 0. And so let's go ahead and use our calculus techniques in order to prove that it's 0. Okay, the math, we should be able to do the math and show it. Well, here we notice that our power of x differs by 1. And so that screams a u substitution. So let's go ahead and try u is equal to x squared plus y naught squared. That means that du is equal to 2x dx, or that du over 2 is equal to x dx. And so we can take those two ideas and substitute it into our equation. I will go ahead and flip to the next page. So take a brief mental snapshot. You notice that, okay, well, negative k lambda, go ahead, take the antiderivative. And you'll notice that the antiderivative of this expression is negative u to the negative 1/2. So you can imagine taking the derivative, the negative 1/2 comes down in front, giving me a positive 1/2, and I lower the exponent by 1. And of course, we're evaluating from negative L over 2 to L over 2. These are the x values. So I didn't change the limits of integration when I did the u substitution. That's me. You could have gone through and done that. What I prefer to do is to simply substitute back in the expression for u. So I'll take that negative sign and cancel that negative sign. So I end up with a positive. And so I get positive x squared plus y naught squared, square rooted. And don't forget, this is 1 over, evaluated at the endpoints. Well, you can see what's going to happen. Okay, lambda. I will go ahead, for sake of argument and completeness, we evaluate at the upper limit, which is L over 2 quantity squared plus y naught squared, square rooted, minus the lower limit. And here you can see the symmetry, the fact that the function was... Oh, that's interesting now that I think about it. I'll have to double check. That might be the case. The integration of an odd function ends up giving you an even function. I imagine that means the integration of an even function gives you an odd function. Ah, that's how the calculus works. Oh, it's always nice learning something new, eh? Right? I integrated an odd function, which gave me an even function. Because the function is even, and I have a symmetric interval, that means that when I evaluate at the upper limit and the lower limit, it's an even function. That means that I get the exact same value. And so you can see when I do negative L over 2 squared, the negative sign disappears, and I get L over 2 quantity squared. And you notice that the first term is exactly equivalent to the second term. And so, without having to specify values of L and Y, you get 0. Sweet. Cool. Well, unfortunately, we're not done yet. Remember, the whole point of the video was to do all the integrations and show that Gauss's law works, but we say that the electric field, the component of the net electric field in the x direction, is 0. Well, we now have to tackle the y component, right? Don't forget, we can't lose sight. Yeah, Greg's got some bylines about even and odd functions, but we have to go back and say, hey, we're not done yet. Okay. And so we still have this second piece to go ahead and integrate, namely the y component of the electric field. Well, we can do the same song and dance, roughly. K and lambda are constants, so we can pull those out. And we have y naught dx, all divided by x squared plus y naught squared to the 3/2. And we notice again, u substitution is not going to work. We start running through a list of different integration techniques. And the fact of the matter is, because we have two quantities squared, square rooted, that screams a trig sub. So let's go ahead and draw out a triangle. I know you guys are probably faster at this than I am, but the reality is that drawing the triangle and then remembering what subs you're using where, the triangle is just kind of a note to yourself about what substitutions you're making. We'll go ahead. Well, first of all, I notice I've set up my triangle like this. It doesn't matter. It won't matter where you put stuff, okay, as long as you remember the Pythagorean theorem. Right. But I notice that how I have my triangle set up, sine of theta is equal to y naught over x squared plus y naught squared, square rooted. And so you notice that that is one of the integrands here. I have k lambda, the integral, I'll make that substitution. So I get sine of theta dx over x squared plus y squared. I'll put to the 2/2, just for sake of bookkeeping. Well, now, if I want to do that trig substitution, I also have to replace this dx with a d theta. And so I need to find the appropriate expression for that. I'm going to go ahead and differentiate this expression. And so I end up with something that says cosine of theta d theta dx. And over on the right-hand side of this equation, well, y naught is a constant, so I have y naught. And I can imagine you could do the quotient rule, low d high minus high d low. I like to think of this as just having a negative exponent. That's me personally. It's just easier to do the power rule in my humble opinion. So I have x squared plus y naught squared to the negative 3 halves, right? Because negative 1 half, decrease it by 1. And then I need to do a chain rule. So I did a power rule, now I got to do a chain rule, and so I pick up a 2x. Which doesn't look good. It looks like I haven't really done anything, but if I keep simplifying dx, we notice a couple of interesting things. First of all, oh goody goody, the 2 cancels the 1 half. Another thing that we notice is that I will go ahead and split this up. I have something that looks like y naught over x squared plus y naught squared. And again, I'll write this as to the 2 halves. And then that takes care of the y naught, that takes care of 2 of those. And then I have an x over x squared plus y naught squared to the 1 half. But look, that second term, if I go back and look at my triangle, this second term is cosine of theta, which means this cosine of theta cancels out that. And so I get something that says, now I'll move the y naught to the other side, I'll move the dx. I get something that says d theta divided by y naught. Don't forget y naught is a constant, how far my field point is from my wire. And I get it equaling dx over x squared plus y naught squared to the 2 halves, which was the exact thing that I need to replace in my integrand. So let's go ahead and do that substitution. I end up with something that says k lambda, the integral of sine of theta, d theta, all divided by y naught. That's it. Now we're off and running like a bale of turtles. We have sine theta, d theta, and you say, no problem. Don't forget, I want the antiderivative, not the derivative, right? Antiderivative. Right? It's common to accidentally do the derivative rather than the antiderivative. So here, the antiderivative is negative cosine. Well, if we go back and look at our handy-dandy triangle, you will recall that based on the setup I had, that cosine was x over x squared plus y naught squared square rooted. Right? And now I'll explicitly write the limits of integration here, since those were in the x. There we go. Well, now we'll go ahead and evaluate at the limits of integration. I feel like I might have dropped a negative sign somewhere. That's okay. We'll keep going. Because we have here, again, we have L over 2 divided by L over 2 quantity squared plus y naught squared, square rooted. Right? And then we have minus a negative L over 2 over negative L over 2 quantity squared plus y naught squared square rooted. And here you notice I have a negative sign and a second negative sign, so I'm minusing. So I get a plus, a positive. So at the end of the day, I get that the total electric field in the y direction is equal to negative k, excuse me, I don't know why I wrote an L there, negative k lambda over y naught times the quantity L over 2 times the quantity 1 over L over 2 squared plus y naught squared, square rooted, and I have 2 of those. 1, 2. And that simplifies down just a little bit. It's not big. Of course, I get a 2 and a 2 canceling. And so I get something that says that the electric field in the y direction is negative k, Coulomb constant, charge density, lambda, L representing the length, the total length of my wire, divided by y naught, and then I'll go ahead. It's ugly, but I guess I'll put L squared over 4 plus y naught squared, quantity square rooted. And you can see, I'm like, wait a minute. I'm confident that we've done everything right, but you can see why Greg is like, wait, I think I dropped a negative sign. If I go back and look at the original situation, I was thinking of the wire as being a positive charge density. But at the end of the day, this tells me that the electric field points towards the wire, not away from it. We know it should go away. So it makes me wonder, have I dropped a negative sign somewhere? Well, we could go back and double check. Field point minus the source. So I get field point is at y naught, source is at x. And so you can imagine if I'm at this source, I got to go back a negative x and then up a positive y. So that doesn't seem to be the situation. I think that we have calculated this correctly. All right. That tells us that, say, if I'm right here, the electric field should point in the negative x direction and the positive y direction. I agree with that. So it looks fine there. Perhaps I dropped a negative sign when I was doing the... Ooh, there it is. You see where it is, right? Sorry about that. It's always good to double check your stuff. Right here. Let me highlight it in yellow. Right? Maybe yellow's not good, but I'll blur it in or something. Right there. See, there's a negative sign right there. But Greg insisted on the next line. Greg dropped it. Right? There should be a negative sign there, which means there's a negative sign here. It's always good to trace through the example. So when I did this substitution, I pick up a negative sign. Well, a negative sign's constant, so I'll pull it out in front, and I get a negative and a negative, which means the negative sign that comes from the cosine should combine to give me a positive, which means this is a positive, which means that's a positive, which means that's a positive, and now order is restored. Yeah, I could have edited that out, but I want you to see when you get to the end of a problem, you should always ask yourself, does that make sense? And I can see immediately there's a problem, but I also know, or maybe not know, but I can also figure out this is not, I won't say a minor problem, but this is a problem that doesn't require me to redo the entire problem. I can find where the mistake is, and that mistake, I can easily track it to see how it would change the final answer. Okay. So I'm leaving that in there. That's always good. So now, incidentally, this is for a finite wire. There has an endpoint L. Okay. But an interesting question is, what would happen to the electric field in the limit as L goes to infinity of this y component? Well, let's go ahead and take a look. If L goes to infinity, then you can look at this and you say, well, if L goes to infinity, then L squared over 4 is much larger than y naught. And so we could imagine, we can just basically ignore the y naught. So you get something that says the limit as L goes to infinity. Well, you get something that says k lambda L, all divided by y naught, L squared over 4 square rooted. But wait, there's more, right? Well, I can take that square root now, and because I have a compound fraction, you can think of this as the limit as L goes to infinity of k lambda L, all divided by y naught L, and there's a 2. But then you say, hey, well, that's interesting. The L's cancel. And so I get that the electric field the y component of the electric field ends up being something like 2k lambda over y naught. Now I'll go ahead and I'll substitute in the expression for k in terms of the permittivity. So this ends up being 2 lambda over 4 pi epsilon naught times y naught. And lastly, you can see, oh goody goody, a 2 and 2 cancel. At the end of the day, for an infinite wire, I get that the electric field is lambda divided by 2 pi y naught times epsilon naught. Good? Awesome. Okay, well, let's go ahead and do this the other way, namely using Gauss's law. So I have my wire, my charge distribution. I have my field point, again, at some distance, y naught. And here, what I am going to do is I am going to choose a Gaussian surface that mirrors the geometry of my charge distribution. And in this case, it will be a cylinder. I'll do dashed lines to say that it's going behind. So you can imagine that there is a cylinder here that wraps around, and I want to make the radius of that cylinder equal to r y naught. So I've drawn it slightly too small here, like this, so that my field point is right on the body of that cylinder. Well, let's now get an idea for the total flux through that Gaussian surface. And we bear in mind that because of the distribution being infinitely long, the electric field, which I will draw in green, has no component in the x direction. Okay. You say, why? Well, you can imagine at any location in space, because this line is infinitely long, at this field point, there's just as many small charges to the left of that field point as there are to the right. And so, again, it's a symmetry argument that the electric field due to that little piece and the electric field to that little piece, the x components will cancel and the y component will add. Or I guess if you're out in the front on that cylinder, it would be the x components cancel and the y and z components will add together. So the electric field due to this infinitely long wire is radially outward. And when I say radially outward, I'm thinking about away from the wire. So if we were to look at this edge on, if we were to change our vantage point, okay, you could imagine this little charge distribution being a dot, right? We're looking down the wire. And what we would see is that the electric field would emanate radially outward from this thing, directly away from the wire. There would be no into the board, out of the board component to this electric field. Well, good. So if we want to apply Gauss's law, we need to find the total flux through the body of our Gaussian surface. And you notice that that's comprised of 3 different pieces. Piece number 1 being the right end cap. So you could think of the flux through the right end cap. You could think of the flux through the left end cap. And you could think of the flux through the body of the cylinder. Well, let's tackle this right end cap. We've already argued that the electric field is spreading radially outward from the wire. And let's also think about what is the unit vector, the direction of normal for that end cap. Well, the unit vector has to be perpendicular to the surface and away from the interior. So n hat is represented by this purple arrow. But you notice immediately that the direction of normal is perpendicular to the direction of the electric field. In other words, right? My normal is this way, but my electric field is in this direction at any point. None of the electric field actually goes through that right end cap. You say, but wait, Greg. Yes, indeed. The same argument could be made for the left end cap. The n hat is pointing in the negative x direction. The electric field is pointing in the YZ directions. And so nothing passes through that left end cap. So immediately we can say that these two fluxes are zero. And so the total flux through our Gaussian surface is simply the flux through the body of the cylinder. Well, let's keep going. Let's go a step further. Because the body of the cylinder, excuse me, I keep changing colors here. Because the body of the cylinder, we'll draw it in light blue over on this right paragraph, or right section. The body of the cylinder is equidistant from that wire, that central wire. What can you tell me about the magnitude of the electric field if every single part of the body of the cylinder is the same distance away? Good. Has to be constant. Furthermore, you can tell me that not only is the electric field constant, but it's pointing radially outward. In other words, E can be written like this. Let me make sure that looks like a hat. Good. Well, let's return to the idea about the normal. What direction, say on the top right here, there's a little patch of area. What direction is the normal vector for that little piece? You say up. Good. Well, how about for the little piece right here? Down. How would you describe the direction of the normal vector at every location on the surface of this cylinder? Also radially outward. Good. And so let's take all of those ideas and let's put them together. The total flux is the flux of the electric field through the area, and I'll subscript this body. We're not talking about the end caps anymore. We're talking only about the body. And the direction normal, we've made an argument, is radial outward. So I will go ahead and replace this. We can say the electric field is constant because every point on the body is the same distance away. It points radially outward. I have the area element of the body, and that is also radially outward. Well, r hat dot r hat is 1. So I have that the magnitude of the electric field and the surface area of the body of the cylinder. Well, I won't go through and do the double integration anymore, but at the end of the day, we have the total flux. Excuse me, I almost wrote body there. The total flux is the magnitude of the electric field times 2 pi. The radius of that cylinder, we use the variable y naught. And then the length of the cylinder, I'll use h. Not to be confused with L. We used L previously, I'll use h here. I mean, L for the length of the charge distribution. I'm going to use h to represent the height of my Gaussian surface. Now we're at a point where let's go ahead and apply Gauss's law. Gauss's law for the electric field tells us that the total flux is related to the amount of charge that is inside the Gaussian surface divided by epsilon naught. Well, we now have an expression for that flux. It is the magnitude of E times 2 pi y naught times h is equal to, well, now we go back and think. I have a linear charge distribution, and the amount of charge inside the Gaussian surface is proportional to the height of the cylinder. The height dictates how much of the wire I encompass. And so here, the charge enclosed is simply my charge distribution times the height of the Gaussian surface. We have a goody-goody moment. Oh, goody-goody! The H's cancel. And so, as promised, I said oftentimes Gauss's law is used to find the value of the electric field. And so we have something that says lambda divided by 2 pi y naught epsilon naught. The magnitude of the electric field due to an infinite wire is simply the charge density of the wire times 2 pi y naught epsilon naught. That should look familiar. That's the same expression that we had doing the direct integration. Pretty cool, huh? Now, yes, you say, I got the same answer. Generally, using these infinite distributions, Gauss's law will be the faster way to go at it. Okay? I will agree, excuse me, that if you do not have a finite wire, then you'll have to, if you do not have an infinite wire, then you'll probably have to go back to the direct integration technique, right? If I have just an finite wire, here is the answer for a finite wire of length L. Here's the answer for the infinite wire. But again, even if you have a finite wire, if you are close to that finite wire, you can start treating it basically like an infinite. This pencil looks infinite to me the closer it gets to my eye. Okay? Well, I think that's plenty for this lecture video. Again, just some example problem to show you that direct integration and Gauss's law can give you the same result. But I think we would argue that Gauss's law was much faster than having to go through and set up all the integrations and deal with the vectors. So, good. Well, I thank you for your attention. Keep up the good work. I'll see you next time.